Okay, this is Ben the Tutor, and this is my video with the answers to my energy practice test. I'm just going to begin talking a little bit about practice tests just for a moment. So, I believe that a practice test is the fastest way to study for your unit test in any physics or math or probably chemistry topic too. So setting aside 1 hour to do a practice test is the best, most efficient way to help you study. It's not the only thing you should do, it's the first thing you should do. So when we take a practice test, we should always go to a quiet place with no distractions. Try and create an environment like the test, so there's no phone, no computer, no people around. And you also have a formula sheet and a calculator. When you do the test, you should do the whole thing with no answers. That is, you just have the questions, do the questions, and give yourself about an hour. I've tried to create a test that would take you about an hour. And you create a test-like environment. So you do the whole thing, and then afterwards you go look at the answers. And if you've got some of them wrong, then you come watch this video. Here is the practice test. So if you're just watching this video and you don't have the practice test, it's here. And I'll have a link to my website in the video below, and you can download this 6-question test on the website. So let's go through the answers. Okay, question number 1. So there's a curling theme in this test, that is ice curling. An 18-kilogram curling rock is thrown. So these are those curling rocks like that, and that's 18 kilograms. This is thrown, so it slides up an ice mountain slope of 36 degrees. So it's going up, a slope like that, that's 36 degrees. It is thrown with an initial speed of 16 meters per second. How high above the ground does it travel when it comes to rest? So this is an energy test. So the key equation is the total energy initial equals total energy final equation. So there's potential energy initial and kinetic energy initial, and potential energy final and kinetic energy final. So when it comes to rest, it's the point when velocity is 0 and it'll then come back down the mountain. So our initial potential energy is 0 and our final kinetic energy is 0 because the velocity equals 0, and here the height equals 0. So the kinetic energy initially is equal to the potential energy final. Remember that kinetic energy has this equation, 1/2 mv squared, and potential energy has this equation, mgh. So 1/2 mvi squared equals mgh final. So the question is, how high does it get? So hf equals v squared divided by mv squared 2mg. And actually, we can cancel the m's. So v squared over 2g. So putting that into my calculator, 16 times 16 divided by 2 divided by 9.8. Wow, my calculator's having an issue. All right. So I got 13.06 meters. We round that to 2 sig figs, that's 13 meters high. Question number 1. Question number 2. The same curling rock is now sliding up a wet road, sloping 36 degrees up. It's the same angle and like that. but it's a wet road. It is thrown with the same speed, 16 meters per second. As it travels, 320 joules of energy is lost to friction. How high above the ground does it travel this time? So in this case, as it travels, there is heat lost or energy lost due to friction and heat of 320 joules. So the same equation, total energy initial equals total energy final. We have potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. We have another term here, which is heat lost. That's added on this side. So again, potential energy initial is 0. Kinetic energy final is 0. So we get kinetic energy initial equals potential energy final plus heat. That's the 320. So I'm going to do it this way. Let's calculate kinetic energy initial, 1/2 mv squared initial. So that is 1/2 times 18 times 16 squared. So I get 2,304 joules. The potential energy final equals kinetic energy minus the heat equals 2,304 minus 320. 1,984 joules, and potential energy equals mgh. So H equals the potential energy divided by mg. That's 1984 divided by 18 times 9.8. So in this case, we get 11.2 meters, which is the same as 11 meters rounded. So just commenting, comparing number 1, it got to 13 meters high. And when some heat was lost, it got to 11 meters high. It didn't get as high. This question has a thrown in extra question. How far does it travel up the road? So it's how high does it get 11 meters? But how far along the road is this question here? This is just a thrown in little trigonometry question. So it's 11 meters high, and that's 36 degrees. To calculate how far along the road, we're going to call this H for hypotenuse, because this is a right angle triangle. So we need trigonometry. So, TOA. And what's this one? That's opposite the angle. So I need sine 36 equals 11 over hypotenuse. So hypotenuse times sine 36 equals 11. So hypotenuse equals 11 divided by sine 36. Okay, so sine 30, my calculator, 36 sine equals, that's like 11 divided by 0.588. So that's the same as 18.7 meters, and we round to 19 meters. That's a little extra trigonometry question thrown in for the end. So if you get to say this point, you would get like 3 out of 4, 4 out of 5. This is kind of one extra mark. Always remember to do sig figs. Okay, question number 3. The same block is now attached to a rope and hung like a pendulum. There's my curling block there, hung to a rope. Someone pushes on the side of the rock so that the pendulum swings. The rope is taut. To like this. And the rock is at a height of 1.4 meters. If the person lets go of the rock so that it swings back, what is the top speed of the rock? It swings back, and what's the velocity? So this is potential energy. Oh, sorry, we call it same energy formula. Total energy initial equals total energy final. Potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. So in the initial one, the kinetic energy is 0, and the last one, potential energy is 0. The speed initial is 0, and the height final is 0. The potential energy initial equals kinetic energy final. So we can calculate potential energy is mgh equals 18 mass times 9.8 times 1.4. Which is 247 joules rounded. And that will be the kinetic energy final. The kinetic energy equals 1/2 mv squared. So we're looking for the velocity. Velocity squared equals 2 times kinetic energy over mass. So velocity will be square root 2 times kinetic energy over mass. Square root 2 times 247 over 18. So it's easier with your calculator to calculate all this first and then press square roots. 2 times 247 divided by 18. I get square root 27.4. I go square root equals. That's 5.23 meters per second and around 5.2 meters per second. This question is asking for the top speed. So the top speed is the moment when it's the very bottom, it's the fastest. Because it's getting faster, and then as it swings upwards, it starts slowing down again. So at this point at the bottom, the kinetic energy final has the fastest speed. Okay, question number 4. The curling rock is now on a flat ice rink. Just there. A crane picks the rock up. So here's a crane. Picks it up. And it lifts it 15 meters in the air. How much work is done by the crane? So we remember that work equals force times distance. And the force is equal to the force of gravity of the rock. So the work will be the force of gravity times the distance. It's mass times gravity times the distance. That will be 18 times 9.8 times 15. That's 2646 joules. The units of work is joules. And again, we need to round to what? 2600, 2 sig figs joules. Question 5. The crane takes 0.83 seconds to pull the block up. So back to our picture. It picks it up in 0.83 seconds. If this process is 91% efficient, what is the power rating of the crane? And what is the acceleration of the rock? The key equation here is the efficiency equals power out divided by power in. So the power in is what the crane does. The crane, the power in. The power out is what's happening to the rock. So we are trying to calculate power in of the crane. So we get this formula. Power in equals power out divided by the efficiency. So the power out is what's happening to the crane. Oh, I just got a thinner thing. So what's the formula for power? Work divided by time. So we got that already. 2600 divided by 0.83. So 2600 divided by 0.83 is 3132 watts. So the power in is 3132 divided by the efficiency, 0.91. I get 3442 watts, which is 3,400 watts. So there's another question. What is the acceleration of the rock? This is a kinematics question thrown in. So kinematics is a different chapter. A lot of physics teachers throw in these kinematics questions at this point in the course. To do kinematics, we write down the 5 variables: velocity initial, velocity final, distance, time, acceleration. And we say what we have and what we don't have. Velocity initial, all the way back up here, velocity initial should be 0. That's 0. Velocity final, that's what we're looking for. The distance, we know, 15 meters. Hold on here. Yep. The time, wait, sorry, velocity final is the one we don't care about. Distance we know, time is 0.83, and the acceleration, that's the one we're looking for. So you go to your formula sheet, and you look at the questions, the formulas, sorry, and the one that I think is the correct one, that has no velocity final, is D equals, which one? D equals velocity initial times time plus 1/2 AT squared. So velocity initial is 0, so D equals 1/2 AT squared. So 2D divided by T squared equals A. So 2 times 15 divided by 0.83 squared. It's going to be pretty big. 2 times 15 divided by 0.83 divided by 0.83. Just divide twice. 43.5. That is 44 meters per second squared. Wow, that's actually quite high acceleration. Okay, one more question. Someone wants to lift this rock off the ground with a lever system. They put a wooden plank on a fulcrum. The rock is 1 meter from the fulcrum, and the person pushes down on the other end 2 meters from the fulcrum. There's a fulcrum, and then there's a plank, and the rock is here, and that's 1 meter. Maybe we'll do this, 1 meter, and this is 2 meters. The person is pushing down there, and there's the rock there. The person pulls her side down 1.2 meters. Okay. How far does the rock move if she pushes with a 98 Newton force? What is the efficiency of the system? Okay, the first question, how far does the rock move? So the topic of this is mechanical advantage. So how this works is the mechanical advantage equals the length of the long side divided by the length of the short side, which is 2 times divided by 2.0 divided by 1.0. So 2 is the mechanical advantage. That is, it will move 2 times further down than it moves up. So if she moves it 1.2 up, we're going to divide by the mechanical advantage. So the rock will move 0. Oh, wow. 0.60 meters upwards. That's how far it will move up, half as much as 1.2. The other question is about efficiency. If she pushes with a 98 Newton force, what is the efficiency of the system? So efficiency is work out divided by work in. So work out, that's what happens to the rock. And work out and work in is what our friend does. So work out is force times distance, and this will be the force of gravity times the distance. Can I get it darker? So that's the mass of the rock times gravity times the distance. 18 times 9.8 times 0.60. That's the work out. 18 times 9.8 times 0.6. So 105.8 joules. The work in is force times distance. So she's using, it tells us, a 98 Newton force, pushes 1.2. So she has a 117.6 joule work. So the efficiency will be 105.8 joules divided by 117.6 joules. That's 89.23%, but we round it to 2. So 89% efficient is the efficiency of the system. Okay, I hope this explanation made all problems clear, and I hope that this test was helpful for you. So you should have a sense now about which kinds of questions were difficult for you which kinds of questions were easy. And you should make your next practice block to practice the ones that were difficult. All right, bye-bye.